Hello there! We're here on the next Rebel Labs interview with the virtual JAG speaker Aleksey Shipilev. And yesterday he did an incredible session on the pragmatics of Java memory model. And now we are going to ask him a couple of questions. So Aleksey, how are you doing?
Yeah, I'm good. Hey.
How did you like the virtual JAG setup, and how did the session go in general?
Well, it's not the first time I delivered this talk, but I think webinars are hard in the way that you don't see your audience, so you cannot have these instant non-verbal feedback from the audience, and so you have to guess what the people who are listening to you are thinking, and it not helping that there is a lag between the YouTube video feed and IRC. So it's not that instant as I would prefer, I think. But that's the thing with webinars. You cannot do better, I think.
Yeah, hopefully the webinar will reach the larger audience than a regular JAG meeting. And I was there. It was perfect for me.
Yeah, but otherwise, yeah, it really saves the travel time. So delivering even the 3 hours talk and saving a day or two of traveling, it's actually worth it.
I'm glad that you liked it. So we'll go now in a really blitz question mode. So I would ask you a couple of really maybe controversial questions, but I don't want you to go into deep details. Just the first answer that you think is appropriate. Just make it 15 seconds. So when we'll start with the default question that makes people puzzle a little bit. So is computer science a real science?
No.
No. What do you prefer, static typing or dynamic typing?
Static.
What is the worst thing a programmer can do? I'm sure you've seen a lot of weird stuff going on.
Yeah, my job is about looking into the weird stuff. So I don't really know how to answer this question because I've seen so many things that are wrong. So I cannot pick any one of them. I think I think one of the worst thing that programmer can do is to stop learning and stop wondering about stuff and stop trying to understand how the things that he is doing are actually done. So that's, I think, the worst thing. If you stand still, that's the worst thing that you can do.
Not being curious. Okay.
Yeah.
What is your favorite JVM language? That's a tricky one.
Well, I mostly write in Java because OpenJDK is mostly Java. I tried a few other languages, but I haven't got myself into actually implementing the complete project in any of those languages, so I still stick with Java.
Okay, good. And, well, this would be simple. What is your favorite open source project?
Well, I'm biased, but I'm working on OpenJDK, and this is the mega open source project, and they have lots of open source subprojects there. So I obviously like the projects that I do. And otherwise, I am the open source aficionado. I think every computer in my neighborhood here is running one sort of Linux or the other. So.
In the whole neighborhood?
Well, I mean, yeah, in my flat, in my parents' flat.
Oh, any computer that you're responsible for configuring?
Yes. Yeah.
That's awesome. It really is a year of Linux on desktop then.
Maybe.
In some places. So, but you said you were working mostly on OpenJDK, right?
Yeah.
You were a performance engineer at Oracle, and how they call you, benchmarking czar and concurrency bug hunter. Those two titles are actually from your Twitter bio.
Yeah, people have actually called me that. So the things that I list in my Twitter description is something that those are actually the names that I've been called over my career. So
those are fabulous titles. So what do you can you explain maybe a bit longer? What are your what do you do at Oracle? And for example, like what are working on that will go into Java 9, or what are the most challenging or exciting bits that will appear in the upcoming Java 9, Java 10 releases?
This is the upside of open source. You can actually read all this stuff on the internet. And mailing lists are open, bug tracker is open, so you can actually Google, my name and see what I was up to for the for the last year. And you can also see the roadmaps and the features that are supposed to be targeted for Java 9. So Jigsaw is obviously one of the things that is the release driver. There are also sorts of other improvements like enhanced volatiles, value types in some way. Well, they are being developed, but I don't think they're targeted for JDK 9. So all the things that you can pull off from the public internet are actually the things that we are doing internally. So there is no much of the secret of what we're doing.
Yeah, but which of those is the most exciting for you personally? Because like different people work on different, and even in the application space, the features are not equal. So
yeah, so the nature of my job is to follow up on performance things, and so at this point, me myself, well, obviously I support the tools which helps performance work, like JMH and Joel and sometimes JCStress. Feature-wise, and I think this should be a public job already. We are trying to see whether we can compress strings, for instance, so they can, consume less footprint, because the empirical study says that most of the strings that Java application use are actually latent one-based strings. So the characters there are actually fitting in the single bytes. And it probably doesn't make sense to waste the space in character arrays for storing the upper word when it's almost always 0. And this is a tricky thing to get right, because the string itself is heavily optimized. There are lots of intrinsics written for the particular methods in the string. And so if you change the internal layout of string, you have to actually follow up how all this knowledge, VM knowledge about the string's internals propagate into the VM internals, and you do not regress stuff, and you actually improve things instead of regressing them. So this is the project that I am excited about right now. And we are still exploring whether it's worth or not. So there are lots of corner cases which you have to understand before trying to see whether you want to go forward with a feature like that in the ubiquitous platform like Java.
Compressing strings.
Yeah.
I think I saw an abstract or maybe a session of yours about that, but maybe that was in Russian. Do you know if any materials about that is like available, like not maybe JAP itself, but more easily understandable by average developers?
Yeah, I did the talk which was called String Catechism, I think. Yeah, and I did this in English, so it is accessible. There is a public JEP, and there is some discussion for this public JEP on the mailing list and in our JIRA. There is also a report, the draft of the report that we are trying to do to sum up our observations as we are working on the prototype. And there is also a code which you can download and run, even though it's very raw at this point, but it's still a prototype thing. Yeah.
Well, maybe it won't blow up. So let's go into a completely different direction and talk about people a little bit. You're often seen at Stack Overflow complaining about broken benchmarking questions.
No, I made my piece. I'm not doing that. I think there are lots of people who are really into stuff right now. So I see quite a few familiar faces who are replying to this post before I have even a chance to read it. So.
But the thing, yeah, it's getting better probably, and more and more smart people are getting on a train of trying to educate the masses. But like, why do you think there are so many misunderstandings about how performance works or how JVM works? And like, is it something internal, or is it something that we learn at school somehow wrong? Or how should a developer think about performance in general? Like, what are...
So I think it is the intrinsic thing about how humans operate. We tend to simplify things because if we understood that everything is very complex, our heads would explode and we will just sit in paralysis, not knowing what to do because there are so many things that you have to consider. So I think this is one of the reasons why people, why new people think that benchmarking, for instance, is easy, because their mental model is really simple, because they intrinsically do not expect it to be complex. So the part of the education is that we are sharing the scary stories about benchmarking, but what we actually do is we are telling people how complex things are under the cover, so people could adjust their mental models into looking forward to the difficulties there, not just blindly doing stuff. And for performance, and I think that's an advice that you will get from any performance guy: the correctness first, then performance. I actually, had a play on the words. I think it's the Lincoln or Jefferson who said that those who sacrifice a little bit of freedom for security deserve neither. So the same goes for performance. Those who try to sacrifice a little bit of correctness for performance deserve neither. The performance of broken program is undefined. While it might be convenient for people who code JavaScript, it's not for us. We do need correct programs first, and then we need to do performance work. It also, if you are doing performance, you will realize that there are two distinct kind of performance work, maybe more, but I frequently stumble upon two kinds of performance work. First is just you have a very complicated software and you simplify it, and then you gain the correctness, you gain the conciseness of the code, and you gain the performance. The obvious example of that is you are removing your own bubble sorts from your code and delegate to collections.sort. This is one of the things that counts as performance work, because you are rewriting your own code mods, if you will, and delegate it to the known libraries. And you also do all sorts of algorithmic improvements when you realize that here you were sloppy and this particular chunk of code runs in O(n) squared when it could run in n log n. So this is one of the most profitable, I think, performance work that most people do. And there is the second part of the performance work, is when your code is actually nice in a way that it is correct, it looks okay, but you still need more performance. And not many people go further, because in most of the cases, your performance goals are actually just good enough, period. Not every application needs to be high performing. So in those rare cases are actually rare, but the community around them is vocal enough so that you might think that all the performance people do are optimizing this, performance to the extreme. There, you need to go for the low-level benchmarking to understand how all the parts are bound together. What is how the hardware works, how the spec works down to the last letter of the spec. Yeah, but this is, the hardcore part. I know that quite some performance improvements are actually done by the people from the first lightweight performance work. Just, eliminate dumb things from the code is usually enough to get decent performance. And most people should just stop there. Because you are better to invest that time in, in writing more functional tests, in doing documentation support and all this stuff.
So basically what you're saying, that writing sane programs that don't do unnecessary stuff and are, well, algorithmically appropriately complex should be probably more or less enough for the average concern about performance. And so we should not, average developers should not think very hard about like micro optimizations and squeezing last bits of performance.
Yeah, and that's the Knuth gets often quoted with this premature optimizations thing. But the essence of the full Knuth quote is not wasting time on unnecessary stuff. So unless you do know that you have to do this kind of optimization, you don't have to do it. Do something else. Do the things that matter.
Yeah, there is a great life advice saying that every day you should ask yourself if you are doing things that matter or if you're doing something stupid, and then you should adjust your behavior appropriately. So, but let's go back to maybe that hardcore performance work of the second kind that you usually do, working on the JVM level. So, what is your development setup look like? What tools do you use? Maybe like what tools you can live without, or something like that. So just to give us a glimpse into what you do.
So I think my toolset is fairly simple, because the things that you mostly use in my line of work is, your experience and your curiosity, if you will, because that's the things that actually drive your development. Other things are just collaterals. So for collaterals, I don't think I can, at this point, live without high-level profilers. The nature of our work is that we have to profile both native and Java parts, because Hotspot is native part and native libraries are native, and Java code is Java code. So you have to use the profiler which profiles both mostly, and there are not so many profilers that do that. We mostly use Solaris Studio Performance Analyzer, even though it's called Solaris. It actually runs on Linux. I couldn't probably live without Linux, because it is really a developer-friendly operation system, because it provides me with lots of tools to monitor what's going on in the system. From the system level, like, just figure out what the processor spends time on, down to the hardware counter level. And I think everything else is built around that. So, for instance, GMH, which is our go-to tool for day-to-day performance engineering, is the part of our lab environment. This is the tool that lets us to set up performance experiments in some repeatable conditions, and so we can, fire the either high-level or low-level profilers to see what's going on. I use console CLI editors to do simple work. I can probably hack Hotspot in VI or even Nano, because my changes are usually fairly straightforward. The tricky part is to understand what change to do, and you don't really need a complicated editor to figure this out. You just need to figure this out. I use NetBeans for heavyweight hotspot development when I do need to do the intrusive change in the hotspot code. Other than that, so I think, yeah, so the performance guy's job is to, figure out what's going on, provide maybe the reproducible test case, provide the analysis how it works, and provide the suggestions, maybe with the proof of concepts. So most of the things you do is you actually try to understand what's going on.
Yep. So, and maybe the last question for this interview part is, so yesterday at the session you mentioned a list of books that people could dive into to understand more about the memory models in general, Java memory model, and obviously concurrency interest mailing list is a good place to start. Maybe you can give, I don't know, 1-2 more sources of information that people can really lurk at for a little bit of time and then start maybe understanding things better. So how would a novice engineer get into the performance world? Or just follow you on Twitter is enough?
I was reflecting recently on that, and I realized that there is probably no quick start guide for this kind of work. And you get into this by feeding your interest with the things. So if you have the particular problem, and you want to understand this in depth, you just dig in. That's it. You use Google, you use any other source that help you to get the material to understand the domain. So for concurrency interest is kind of an interesting list because you have both trivial and non-trivial discussions there, and mostly people are providing the citations and links to the existing research. So that's probably the good way to introduce yourself to the fine art of concurrency. The books that I had recommended actually has the list of references for the existing human knowledge about the domain. I do know there are performance, user groups, for instance, or mailing lists which have the experts lurking there and sometimes discussing high-level things. So I know Peter Lorre maintains performance Java user group community. There is the Mechanical Sympathy by Martin Thompson. And I think many interesting discussions are also happening on the OpenJDK mailing lists, but those are mostly implementation centric.
Well, that's a fair answer. I personally really like that there is no easy way to get into the area.
Maybe I haven't reflected on this enough, but that's how I got here. It's not some magic book that I keep under my mattress that actually turned me into the performance guy. It's not like that. You just do stuff and you learn as you go.
It's a great moment to say thank you, Aleksey, for this interview, for your very insightful answers. And as we are currently at the moment where we go into actually doing stuff and looking at stuff, we will continue with looking at a couple of examples of how JCStress library can organize tests for concurrency issues and create test cases for different concurrency issues. But at this moment, I would like to say goodbye to those of the people that are listening to us on the Virtual Jack podcast. Thank you for joining us. And if you want to continue seeing this, be sure to go to Rebel Labs, where we'll publish this interview session and a Virtual Jack session recap in the closest future. So, podcast people, thanks a lot.
Yep, thanks.
People who are still with us on this video, we are getting into the hardcore concurrency performance engineering area. And Aleksey promised us to show a couple of examples of JCStress. Maybe you should just drive us through what JCStress is, I would say.
All right. I think it's better be done by example. So let me first share an example. So remember in the talk yesterday, I said I had the example with this, bit set word tiering stuff, and I asked the question if two threads are writing into distinct positions in the bit set without synchronization, can actually third thread observe both the writes or under some circumstances you can actually experience something like word tiering. So JCStress is one of the harnesses that we had developed to simplify writing these test cases against the real implementations like that. We mostly used it for the low-level work, so it's not usually about the library. It's mostly about really how VM treats the particular elements in the language and some core classes. But it's also useful to do this kind of one-off functionality research. So what do we do here? Here we have a class which is called bitSetTest. It's annotated by this magic annotation JCStress test. That's just a marker annotation. It says that this instance is a state, which means it has to be instantiated by JCStress and it bears some state. It has to, so here's the part of the state. Here's the bit set, which is the part of this state. And here are two actors. An actor is also the JCStress annotation, and each actor method would be called by a distinct thread concurrently. So what this test does, it says, okay, you have an instances of bitset tests, which has their own bit sets. Spawn two threads, and run each method continuously in one of the threads, and call it continuously, so that two threads will concurrently try to set element 0 and element 1 in that bit set. So for each state, I think we are calling the actor method only once. And we have the special method, which is annotated with arbiter annotation, which says that after both threads are finished with the state, somebody else should run observe method, and it will read the locations that we had written in the worker threads and store the values there in the special result object. And so the harness will then instantiate lots of these bitset instances, rendezvous the worker threads on this bit set so they can concurrently do stuff on this set. And then it will, for each this state after both worker threads are done with it, it will collect what the arbiter thread had observed. And then by observing what results do you get from this test, you can actually see what was happening. And we can provide the grading for that with this outcome annotation here, which says that if I got, for instance, true false, which means that R1 is true and R2 false, that means that the thread 1 had intervened and word tiering occurred. That means that the thread 1 concurrently done the work with thread 2 and overwritten the adjacent bit that thread 2 had set. Conversely, when you get false true, you have the thread 2 intervened, right? And if you have true true, that means that the both writes are observable. So we talked about this yesterday, that if those were two distinct fields or two distinct array elements in the Java language, then Java language will provide me with the word tiering guarantees. It will say that the operations on this distinct element are really, really distinct. So these two outcomes are not acceptable in the Java language. But bitset stores the bits densely in the integer or long arrays. I can't quite remember it at this point. And so when you do the concurrent writes, you can experience the word tiering-like behavior. And I can use this example to demonstrate this is not a theoretical construction that actually happens. Let's see how it goes. So I have compiled this test. Let me run it. Let me run it like this. The test is in the package vjug, and it's called bitset test. Let me run it. So already we can see that harness around this test continuously, and it says that 128 millions of times we had actually observed both elements set to true. But we also have not that rare occasion that one of the adjacent bits were rewritten by one of the threads. So this is what is the essence of the word tiering, that bitset, unsynchronized bitset, sets us up. So this is not a theoretical thing. If the language allowed us this kind of behavior for the field writes or array element writes, you will have a very interesting class of bugs that you will have trouble following up and reproducing and ultimately fixing. So this is why GMM forbids word tiering.
So,
any questions?
So JCStress runs the test case that we specified and annotated with what threads would be actually acting and how to combine the outcome. So the test structure is really similar to the diagrams that you showed us yesterday on the session, where we had the state initialization on the top and different columns described what different threads will do. So this is very similar to that. But and
because that's a very natural formalism.
Can you say a little bit? So obviously under stress, like when there are many threads mutating the state at the same time, there are different side effects coming out. But like, does JCStress also try on the not so loaded environments? Maybe my code is working really well when the really tons of threads trying to do something, but on a single-threaded environment, this is, well, let's say 2 threads doing something. It's not that. So does JCStress cover mostly all interesting cases that I should care about? So if I come up with a concurrency primitive, and I would be like, oh, this is how it should behave. All I have to do is just to create a test with JCStress and specify the outcomes to see if actually it behaves more or less as I predicted or not, or should I do something else as well? I mean, do you know any situations or setups which might occur in reality, but JCStress doesn't try that?
Well, I will conservatively say yes, because JCStress covers the limited set of scenarios. But your question is actually akin to the question of, if I have new method in my library and I try to write unit tests, what should I write for the unit tests? That's a really generic question, right? You have to understand how your primitive work if you do white box testing, for instance, or the gray box testing.
Well, yeah, that's true.
So we have, first, in JCStress, we have the set of experimental tests, again, say atomics, which try to do different things on atomics that we expect to cause trouble in the naive implementations. So this is the white box testing for you. So you can learn something there, but there is no silver bullet, right? If you have to actually write the specific tests for your specific primitive, understanding how the specific primitive, what are the specific failure modes for your primitives.
Yeah, that's fair enough. The code looks really concise, using this tons of annotations. I like it a lot.
Yeah, I have three more examples which are more interesting. Bitset is not interesting because arguably what I do is not, is actually violating the contract for Bitset because it says that you cannot use it without external synchronization. That's it. But let's do something more both legal and illegal. Let's say all right, atomicity, I think. All right, atomicity. And I also did this observation that if you want your memory accesses to be atomic, you probably have to maintain the alignment constraints for the reads and writes that you are doing. Because misaligned accesses could actually be not atomic on some hardware. x86 is known that if you are doing the access that spans the cache line, that's not atomic, unless you do the lock prefix, which will cost you a lot. And there's the separate issue. I did that once. There is a link on Twitter somewhere. So this test says, let's do something really weird. Even though we are in Java, let's allocate the slab of raw memory and try to read and write and some misaligned access there, misaligned offset there. So what it does, it says, okay, let's allocate the 1 kilobyte block. We will get the address of that block in ADDR. We will mem set it to null, and then we will get the offset. But the calculation of offset is actually is rather tricky. So this this expression here aligns the address to 256. Do you agree? Because it strips the lowest bits.
Yes, it does. So we negate 255, which means it will have like higher bits set and lower bits not set, and we logical end that with
rounds down to this boundary.
Yep.
So if I run just with this offset, then the accesses that I will do at this offset would be would stay within the cache line, regardless what is the actual cache line is, and as long as it is the power of 2. Right?
Yep.
But it gets tricky if I say subtract 2 from that. Because now, if I read 4 bytes, I will cross the cache line. Because the first 2 bytes would reside at the end of the previous cache line, and the other 2 bytes would be at the beginning of the next cache line. So if I read the 4 bytes of this offset, read or write, I will cross the cache line. So indeed, I do that in my actors. I put the int at this offset, and I put -1 there. But this is more understandable for me, just all ones there. And the other thread reads from that offset. Okay? So for the outcomes, we naively would believe, right, that the usual outcomes is 0 when actor 2 runs first, when actor 1 had not really written the value yet. Or -1 when the actor first completed and actor 2 had not yet run, right? Well, yes, it ran after actor 1. But we also probably, if we indeed have the breach of atomicity, we will have something else there. So let's see if it goes that way. So it's called unsafe atomicity test. Okay. And right now, you can see that there are 2 other results there, which are arguably rare, but they are still there. If you...
Yeah, they are very rare. I mean, like 7,000 out of 10 million.
Well, if you're running your production system and 10 million operations per second, that means this event will happen every second. So it is probably a bug every second.
That's true.
So, and you can, if you figure out the bit masks for these values. It is as if the value is stored in the middle.
Yep. It's
so
exactly
this
like
thing with misaligned accesses. They lose atomicity. You have to do aligned reads for the atomicity stuff.
That's really interesting. Actually, it's a great example. I wouldn't predict that like from the top of my head. But this is something, not something that the average Java developer would encounter.
Yes, unless you believe that you are, capable in doing your own off-heap solution.
That is true, and I know a couple of products that do off-heap manipulations. Like they should be very precise with what they do there. That's a great example. Do you want to show us something else?
Yeah. Let's see. This is a really low-level example how hardware works. This is what you will face if you break from Java into this unsafe wilderness there, or just write in C or C++. So let's get back to Java. Let's first see. I don't think this test, and this is called unsafe publication. And people, when you call them, when you explain to people that you really have to code to spec, so you have to really synchronize accesses so that all the proper happens before relationship would be established. They come up with their own tests which show that nothing bad is happening when you don't synchronize. So this is the counterexample which says that bad things happen if you don't synchronize. So what do we have here? We have some object O, which is just my object. My object is the class which has the single integer field x. So what this test does, it says, okay, we have the instance of this object O. We write a new value of x there, and we publish it via the race. Notice there is no volatile here, so if I read this object in my consume method, that means I do the race read. And so if I then observe, try to observe x, I actually have a question from the memory model standpoint, what could I observe? So if I put volatile here, what I could observe is either -1, because I could just run my consume method before publish, right? And I could observe just null.
Exactly.
Or I could observe 1 here, right? So the local O is not null, so I read x from there, and all that happens before relationships are transitively, go between the threads, and I observe this write. But if I don't have volatile here, this read is actually a racy read. So it could also observe 0, even though I observed the myObject instance. So my object instance was published, but I could not see the contents there. So let's run it. Run it, and run it, and run it, and run it, and everything is fine. We can only observe 1 or -1. And then you get back to the speaker and said, well, all the things that you have said about the happens before is wrong. See how this code is working perfectly well without volatiles.
Is it a case of works on my machine excuse? Should we try?
This is x86, and this is the very lucky coincidence that we have this on x86. It's not actually guaranteed, even on this platform. It just so happens that we don't observe this value. Let's do other thing. SSH. I have my own small ARM machine. It is ARM v6.
Okay.
So let's run this test there. I just copy-pasted. Oh, I think I need. And this is ARM.
Indeed.
Oop, something's wrong. Oh, anyway.
Well, this is ARM. It's not.
Demo gods are angry.
Indeed. So how many architectures do you usually test the generic performance things or generic concurrency things for OpenJDK?
I can't really say.
You can't, like, because you don't know, or is it kind of private information?
It's not public. So.
Okay. Fair enough. Fair enough.
All right. So you can actually see that you can observe this under constructed. Well, this is not under constructed object. You can actually see that even though you observed the write of the object, you do not observe the write into the objects. So this is why, if you don't have volatiles here and you rely on the races, then you are setting yourselves for surprise. You can probably pass the unit tests on your continuous integration machines, and then you have users where your code will break spectacularly because they have another architecture or more sophisticated compiler or anything like that. So code to the spec, not to the implementation.
That's a great advice.
All right, and last thing, if you don't have any questions on this, I have a last example for
I think we can go into, this is a very fascinating test, but it's, well, the code is really concise and kind of short, so
I think it could be made simpler. I don't really have to have my object. I could just do the two separate fields, but it is aligned with the next example.
That's great. Let's see the next example then.
So the next example says that we have roughly the same. We have my object O, but in the last example, I just had the object already constructed and I update it and publish it. But here, I actually construct the object with some value. And my constructor accepts this value and assigns it to the fields in this object. So this is just constructing the object. And then I publish it unsafely. Right? There's no volatile. So, and I do this thing again in consume. I read the object. If it's not null, I do the sum over the fields. Otherwise, it's -1. So the grading there is as follows. Well, -1 is the object is not yet published and we don't see it. 4 means we had seen all the fields written properly, and everything is in between is, 1 or 2 fields are visible, right? So we know that if we want to publish this object via race, we probably have to make this object immune for this kind of abuse. So we have to make it final here, right?
Yep.
The nature of this example is to demonstrate that the unsafe construction is really unsafe. So let's run it.
I have a feeling that it will be unsafe.
And we run it.
So here we still are at the normal architecture, right? So
yes, it's x86. There is no finals, and what we see here is
that we see that there are no acceptable interesting cases. So we either see the fully published object or don't see an object at all.
Even though the spec says that this unsafe behavior could result in non-zero cases like this, we don't observe them as non-zero here, right? And this is a really, this is just, again, the luck in this particular, how this particular implementation runs this particular test code. So I know that if I turn off the compressed references for this test on x86, I will actually see the under-constructed objects.
Interesting.
Yeah, and what this thing does? It just slightly changed the code generation in the JIT compiled code. The compiler was allowed to reorder reads on the producer side, so it did if it wasn't used compressed oops. And then you have this kind of thing. So you can delude yourself that something is working with simple examples and say that violating the spec is okay because here is my example with with default mode does not exhibit the particular nasty behaviors, but at some point in the future, you will face some, legal optimization or legal, behavior that will obliterate your belief. Right? So if I do finals here,
then you will make the JVM publish it safely.
Yes.
So
let's compile it. Come on.
It just takes a couple of seconds. Don't worry.
If I run it now, it says 0.
Yay!
Just what spec is providing for us.
That is amazing. Those were really interesting examples. Do you have the code available for those available somewhere, or
I think I had pushed them in the samples for JCStress, so it's there in JCStress workspace.
We'll provide a link to those to the classes from the Rebel Labs recap of your yesterday's sessions and the blog post where we'll put this interview on. I feel myself smarter already, actually, so I'm really grateful that you invested that much time into showing examples to us. Do you want to maybe conclude in a couple of words? What do you want developers to think about concurrency, performance Java memory model, or just any general life advice?
Okay, general life advice about concurrency: don't be overly smart.
Yeah.
So do the obvious thing in concurrency. If you want to pull some trick off with concurrency, you really have to know it is correct and it's working everywhere. And if you want to prove that it's working, then you have to do the sorts of low-level things that we were talking about yesterday. But other than that, just code to the spec. Just don't rely on the races. Synchronize everything, and you'll be fine. If you do want to relax some of the synchronizations for better performance, you really have to know what you're doing.
That's a great advice. Do the hard work. Follow the spec. Follow the what intelligent people would do. Ask advice on Twitter or any of the mailing list that we mentioned. Thanks a lot, Aleksey. It was great. Once again, I had very much fun. I hope our viewers will also have very much fun. Thank you. This interview will be published on Rebel Labs today or tomorrow, and I will provide all the links.
All right, cool. Thank you.
Thanks.